All right. I would like to welcome you all to the session on Couchbase Analytics, Unparalleled Performance, and Unmatched Flexibility. This is going to be a tag team presentation by myself and Till Westman, who runs the engineering organization that develops Couchbase Analytics. All right, so I'll be talking about sort of what we're doing in general. I'll give you an introduction, and then I will tell you about Couchbase query engines. We have two, and I'll explain to you what they are and why. And then what I'll do is cover some principles that underlie parallel databases that analytics is built on. And then I plan on handing off the baton to Till, and I will let him tell you about more specifically how we do things under the hood in analytics and show you some evidence that it works as designed, and then he will wrap up the talk. All right, so let's start with the basics. So traditionally, when you look at analytics solutions, what you see is you see a business application, that is maybe doing some business stuff against some operational database. Maybe it's an e-commerce app or something. And on the other far end of this whole picture, you see an analytics tool that would like to know what's going on. And typically what happens is sort of operational things happen today. ETL maybe happens overnight, and the data warehouse now has information about what happened yesterday, and the analysts can do that. So the problem with this is it's a slow process, right? You're getting your information sort of after the fact, hours later, maybe even a day later or something along those lines. So what Couchbase did when they came out with the analytics service was to move to a model where the business apps work on the operational data, but at the same time, the analytics tools can access what's going on. They can actually see the data as it's changing, and this allows you to do real-time analytics and gives you a much faster solution. So that's kind of the basics of Couchbase Analytics, the purpose for it. But something that's important to understand is how it fits into the enterprise, right? So Couchbase Analytics is not a data warehouse. So if we look at sort of the typical enterprise, what we see is an enterprise will have a data warehouse. A particularly modern enterprise might also have a data lake. They might be feeding data into the warehouse and some other data into the data lake, or they may feed everything first into the data lake and then on into the warehouse. And on the right-hand side, we see like BI tools looking at the data sort of more traditionally with charting and things, and maybe data science tools, trying to do some machine learning or data mining on that. And we have our analysts over here on the far right, all of whom are kind of waiting for the data to show up in the warehouse and or the lake. And that data is coming from the left, where we have applications talking to operational databases. So a typical enterprise has multiple operational databases, and this one happens to have made two good purchasing decisions and bought Couchbase twice, one for e-commerce and one for their customer care center. They are doing some social media things, and they bought something else here, and they have some traditional relational data being dealt with back sort of at headquarters. So in an enterprise like this, what can Couchbase Analytics do? So by doing what we saw on the previous slide, what that allows the Couchbase analyst, or the person who would like to start analyzing what's going on, let's say in the e-commerce app, to do, is to sort of move from waiting for, data warehouse, data lake, to looking at the data as it's changing in the operational database. So Couchbase Analytics basically has a copy against which the analysts can do queries and see real-time changes in the data. And we'll talk more about kind of the architecture under that hood. And you can do that, for each of your applications. And so we have two Couchbase apps. We could have two instances of Couchbase Analytics, and the analysts who want to know what's happening sort of on the website or what's happening in customer care land can do that. Along came another feature of Couchbase Analytics, which is the ability to actually sort of consolidate your Couchbase Analytics clusters. So we could actually have a Couchbase Analytics cluster here, and then both of these operational databases could be feeding that cluster. And now, in addition to being able to analyze what's happening here and what's happening here, we can also do analysis over the combination of those things. So someone could now do an analysis and see, sort of there's something happening in shopping land, and sort of the phones are lighting up in customer care land, and try to figure out why by analyzing both of those together. And then in the most recent release, or the second to most recent release, we'll talk about the most recent release in a minute, we can also now reach out to your data lake, and you can do some analysis if you want that covers not only sort of all of your Couchbase operational databases, but also things that may be in your data lake that are coming from elsewhere that you'd like to incorporate into that analysis. So the thing to notice is that we have a bunch of analysts who used to have to kind of sit on the far shore of the data lake, waiting for data to kind of drift across, and now they can get this data sort of more instantly. Okay, so that's how Couchbase Analytics fits into the enterprise. Let's talk about what it offers and how the blue and the gold sort of clusters work. So Couchbase Server actually has two query engines. One that is used for the Couchbase query service, and those of you who are familiar with Couchbase for a while are probably familiar with that engine. Basically, the query service works together with the index service and the data service to give you sort of data management and database capabilities and SQL-like queries over your operational data. And then there's a second query engine, actually, that we're going to be talking more about today, which is for the Couchbase Analytics service. And so that query engine is here. And this is depicting a Couchbase cluster that has 1, 2, 3, 4, 5, 6 instances of basically a parallel query service for sort of these 6 instances, and then 3 instances of the Couchbase Analytics server. So one of the other features of Couchbase Server is you can kind of scale, the different services according to what your needs are. This is just an example here. And the way things work so that the analytics service knows what's going on with the query service data, the data that's living actually in the data service, is that there's a protocol that underlies all of Couchbase Server called DCP, the Data Change Protocol. And so basically, when things change in the data service, as transactions are being performed, the information about those changes is being propagated on that DCP bus, if you will, to the index service, which is listening to keep the data indexed for purposes of being accessible by the query service. And the analytics service is also a listener to DCP, and that's how it knows kind of what the current data is. So how do these two query engines work and how do they differ? So suppose we have someone who wants to do some small operational thing. So they want to know, for example, sort of what's the salary of the employee named Robbie? So that question would be sent to one of the query service cluster nodes. And what that node would do is basically go off and start by taking the name and looking up in the index, Robbie, and finding out that the object associated with that name has primary key E77. And then the query service would go ask for the value, which might be here on this node, of that object and get that value back. And so here we have the Robbie object, at which point the query service can now answer the question and say, sort of $1.8 million is the answer. We may have analysts of the kind that we saw on the right-hand side of the data lake before who have bigger questions, right? So this analyst might want to know sort of what's my spend, on salaries of employees. And so that question is actually going to get answered by the analytics service, and we'll get the answer back. And what we're going to look at for pretty much the remainder of this talk is how does that work, right? So what does the analytics service do when it's being asked to answer a big question? And notice that we have this cluster with these sort of nodes here, these nodes here, and they're not on the same node. What this allows is these questions can be asked and the resources of these nodes can be devoted to answering without disturbing the small sort of rapid fire things that are happening on the other side, on the operational side of the house. Okay, so that's a little bit about Couchbase Server as a cluster, as a sort of a two-engine database. And before I turn this over to Till, I want to give you some sort of underlying principles, things that have been learned in the parallel database community that will be helpful as you hear what Couchbase Analytics does. So one of the big things about, big data and sort of dealing with today's data volumes and the data change and things is when your problem size gets bigger, you need to make a decision about how you're going to handle that with the performance that you need. And so there are basically two things you can do. You can buy a bigger server, that's called scaling up, or you can scale out by basically having more pieces, and we'll look at that as a solution. That's how Couchbase Analytics does things. And Parallelism comes to the rescue in terms of being able to answer queries over larger and larger problems by scaling out. So what Couchbase Analytics did was to bring to bear sort of on the world of NoSQL, things that have been known for quite a while in the world of parallel databases and data warehousing. And so the architecture, the basic architecture that Couchbase Analytics is based on has often been called a shared nothing architecture. Basically, it's made up of a bunch of nodes which have their own processor, memory, and disk resources. And the way you scale out is you decide to get more nodes. Okay, and so this has actually been done for quite a number of years. In the 80s and early 90s, there was research in parallel databases, sort of a bunch of famous systems listed here, lots of commercial examples of data warehousing, data analysis platforms based on this architecture. Teradata, the big gorilla, IBM's parallel offering, Microsoft's Vertica, one of the newer comers, Redshift, and the Amazon cloud. Basically, over 30 years of R&D have gone into this being a really good way of doing parallel kinds of query processing. And so we employ these best practices in Couchbase Analytics, as you'll see. All right, but why? We talked about, sort of scaling out. What might I want to have happen when I scale out? So one thing that I might want is I might want fasterness, right? I want more speed, right? I'm not happy with how long it's taking me to find out what my salary spend is. And so what I'd like to do is buy more nodes and have things get faster, have performance get better. And if performance gets better kind of linearly as I add nodes, that's called sort of ideal speed up, linear speed up. The other thing I might want is, maybe I'm happy with my performance, but, my business starts to boom and now I have to deal with twice as many customers, twice as much data. The size of my problem is growing. And if I'm happy with my performance, then what I want when I scale out is for my performance to remain the same as my problem size grows. So let me keep flat performance. And so let's kind of drill into that a little bit. So linear speed up is said to be achieved if, like adding, for example, 4 times more resources will give you proportionally faster execution time, right? So if I have 100 gigabytes of data and I want it to speed up by a factor of 4, if I get that speed up by adding 4 times the hardware, then I've achieved linear speed up. So that's one of the objectives you might have as you scale your system out. The other thing that you might be wanting, as I mentioned on the previous slide as well, was you may want to add resources to just handle more data, right? So if I start with 100 gigabytes of data, and my business booms and now I have a terabyte and I'm happy with my performance, then I may want to throw, sort of 10 times the hardware so that I can maintain that same level of performance with 10 times as much data. And that's called batch scale up. Another kind of performance improvement you might want that's more on the operational side is called transaction scale up. And that's when you have more concurrent requests, more users, and you want to handle them without loss of performance. We're going to be focusing on these forms of sort of performance improvement in the rest of this talk. How do we achieve that? Well, the answer is, as I mentioned, parallelism to the rescue. And there are 2 kinds of parallelism that you'll see when Till tells you more about how Couchbase Analytics works. One is called partitioned parallelism. So the idea is, sort of each node has a shard in modern terminology or a partition in older terminology of the data and the index and so on. And so you put many machines together and you harness that sort of the aggregate power of those machines. And then when you have a query to answer, you basically set all the machines loose together on their part of that query. So for example, if you're doing some selection, sort of find me, sort of all the employees with these characteristics, that selection could be done in parallel on all of the nodes that have pieces of the employee collection. Okay. The other kind of parallelism that you'll see is called pipeline parallelism. So not only can you be working in parallel, but if you have a query and the query is, doing a selection and then it's doing a join and it's doing some other things, data can also be being passed from one operator to the next operator in this parallel world and sort of pipeline. So that in addition to sort of getting this kind of horizontal parallelism, you're also getting some vertical parallelism. So these selections could be happening in parallel, feeding the join, which could be starting in parallel, and so on. And so that's called pipeline parallelism. All right, so that's the background, right? I told you about sort of Couchbase Server and its architecture and how analytics kind of fits into that puzzle, how it brings a new query engine in, but not much about how it works. And then what are the underlying principles? And so what I'm going to do at this point is turn you over to Till Westman. He runs the sort of the development group that builds Couchbase Analytics. And so he's the best person you could ask for to tell you what's under the hood.
Thank you, Mike. Okay, so let's step under the hood. So before we do that, let's look a little bit at the architecture. So Mike talked about the shared nothing architecture, and what we see here is kind of the high-level architecture of our system, which has multiple equivalent nodes that contain basically all the components that you need to evaluate queries. And that's kind of what we want to see here. Basically, we have this setup of multiple nodes that make up a cluster. And you see at the bottom, you see that we also have storage. And the storage is split up even further. So let's take a quick look at what the storage looks like. So each of those nodes has a number of disks. And on those disks, the data is stored. And it's stored by partitioning the data based on the primary key of the record that we're looking at, and that primary key is the same one that we have in the data service. Then we also have a primary index that follows this hashing, and it stores the primary key together with the data record. In addition to the primary key, we also can have secondary keys that only contain a secondary key and a primary key, so basically to provide the ability to do a lookup. And an interesting aspect here is that the index data is local, so which means that the partition that contains the actual data also contains the secondary indexes for this data, which is different from what the query service does. The query service uses a global secondary index, GSI, while the analytics service uses LSI, a local secondary index. So we have these storage devices here, and they contain the data. And here's a little overview over what that data actually looks like. So for each of those partitions, we have the primary index that I just mentioned. It's based on LSM storage. That's why we have these components here, and we do the same for the secondary indexes. They are also component-based. And so this is kind of the layout that we have. And this is what gives us the degree of parallelism with which we access the system. So every node basically has a number of storage devices that it can use, and then you have multiple nodes. So basically that's how you get to the degree of parallelism that you're looking for. So to illustrate that, let's look at the query execution lifecycle that gives us an idea on how basically the work gets distributed across the cluster. And so the first step, if you have a query that comes into the system, is okay. The application submits a query using the REST API, and on any one of the nodes, any node will work, and we'll just take it. Then it will parse the query, it will analyze it, it will optimize it, and it will create a plan. And again, any node can do that, but once the plan is generated or the job is generated, we'll distribute the job to all other nodes. So now all nodes in the cluster have the same job and know what they need to do on their node. In the next step, what we'll do is we'll execute this job in parallel on all partitions, as you can see. So there's a very decent degree of parallelism that you see here at the bottom. And once each of those partitions has done their work, the result data from each node will be brought back to those nodes from the computation. And then, depending on what the specific operation is, there might be a consolidation step here, or like a final sort or merge, or there might be nothing because we can just get the result back, and that's then the application gets the result back and has evaluated this whole query in a much shorter time than you could do if you were doing everything sequentially one after the other. So to look at a little bit more detail, so basically we said this is the general way that these things work. Let's look at specific operators, how specific operators in the query plan or in the query execution graph evaluate these things in parallel. And so here we have an example. And so the query that we see here is we want to select the brewery ID and the brewery name from the beers collection. And what we want to do is we want to choose all the records where the brewery ID is less than 3. And so basically we have a little example here with 3 partitions at the bottom. And you see we have different beers and breweries with their brewery IDs in here. And as we said, we want to select all of those that where the brewery ID is less than 3. So we do the selection in parallel on different partitions. And we see on the left, after the selection, 1 record is left, and in the middle there are 3, and on the right there are 2. So this is basically the first scan that we do. And then this is basically a global scan that scans everything and gives us just partitions the work into multiple partitions. So this is directly on the primary index. We can also do that using a secondary index. So in this case, the query is slightly different. It's now for the brewery that exactly has the ID 3, not everything that's less than 3. And what you see here at the bottom is our secondary index. And what we will do now to find the records, we will go into the secondary index. We will find all of the index entries that basically refer to the brewery ID 3. from those index entries, we will get to the primary keys. And so on the left side, what you will see is there are basically two records with the keys K1 and K2 that refer to the brewery ID 3, and those two qualify. And the other ones on the other side, you will see that in the middle there's nothing that qualifies. On the right, basically we only have one key, which is K7. And so with those keys in hand right now, what we will do is we will sort those keys so that the keys that we're using to pick up the data are in the same order that they are in the primary index, so that we can very efficiently retrieve the data from the primary index in the right order without having too much search times in between those individual steps. So then what we will do is, so after we have sorted them, we just apply, basically we search for those entries in the primary key and we get the result. So this again happens completely in parallel, and there's no interaction between the nodes at this step, only at the end to get back the result. Okay, another one is, so another operation, which is a little more interesting. This is a parallel grouped aggregation. So what we want to do here is, again, we have the beers data set, and now we want to find out for each brewery, how many beers does this brewery brew. And what happens here is we basically want to aggregate, right, and basically get for each brewery a single number that tells us how many beers there are for this brewery. And so here again, we have the data at the bottom with different brewery IDs. These are all partitioned by the primary index. And so the first step that we do is we aggregate on the brewery ID, which we want to aggregate on locally. So that's just basically, this is just on the same node, nothing specific happens. It's just basically that we do the first step of counting the number of beers for each brewery ID that we have. And once we have done this local aggregation, we basically need to now make sure that we actually get everything that has the same brewery ID, so they're the same node. So we will hash repartition the data, and now basically all of the beers with the brewery ID 1 are on the same partition. All the beers with the brewery ID 2, 3, and the same for 1. So now basically we have all of that partitioned nicely, and now we can do the final aggregation to actually find out that for the brewery ID 2, there are 3 beers here, and you have the other results on the right. So that is a little bit different, right? Because now we actually had to repartition the data between those two steps that we're doing to perform this aggregation. Another, of course, important operation is parallel sort. So sorting, we know, is a very expensive operation, globally speaking. So this works, again, in a similar way here. We just want to order our breweries by the brewery name. We have the data at the bottom. So then what we do a local sort. So now basically we have locally sorted runs of data. And to get to the final result, we will merge those runs in an efficient manner to get all of them into the right order in the end result. And here you basically can see that you have the result containing all of which is ordered by the beer names from ale to Weizen. Okay, I think you're seeing the pattern. So now it gets a little bit more interesting, because so far we always basically only had a single collection of data that we were working with. But of course, you also want to join records from different collections. And so in this case, we're joining the beers and the breweries. And what we want to get out of that is basically pairs of beers and breweries. And so the way this works is, the first step that we do is from the breweries, we take the records and we hash repartition them, so that on each node or each partition, we have breweries that agree on the brewery ID. And then the next step after we have done that, we do the same repartitioning for the beers. So basically now we are ensured that since we have all the brewery IDs for both the breweries and the beers with the brewery ID 2 on the same node, we know that if we want to join them, they will be on the same partition. And so that's what we do. We take both pieces, the breweries and the partition of the beers, and then join them together to get these joint records that match and produce the joint tuples. All right, so that kind of gives us an overview over, how different algorithms or different operators implement this and manage to distribute the work onto multiple partitions. So the other thing that we also support is that we also have external data. So far we talked about the internal data that's inside of the cluster, and we talked about the storage partitions, but now we also have other requirements, like, for example, this one, where we want to read data that is on an external storage device, so not really within our cluster, and we want to run queries on that. And so you see here at the bottom what the external storage content looks like. So we have a directory structure here. There are reviews, and in the reviews directory, there are different years, quarters, and month. And inside of those folders, we have data files in JSON. And so if we want to query those, we'll create what we call an external analytics collection on the top right, on a specific container that contains this data, and it uses a prefix that you see using reviews /2019. And then we also have an include filter there to select which data actually needs to be read to answer the query. So now we want to run a query against this by defining this external analytics collection up there. And so now somebody wants to run a query. We just want to get the number from my 2019 collection. So what will happen here is that we will compile the query. After the query is compiled, we will retrieve the metadata from the external storage, which means that we retrieve the names of the files, we will retrieve the path in which where the files are stored, and we will also retrieve the sizes of those files. And once we've done that, we're coming back. So we have now determined all of the files that have the right prefix, and then we can also apply a filter that we have specified to further reduce the number of files that we actually need to read. And after that, we will assign these different files to different compute partitions so that we can then evaluate them in parallel. And basically, when we create those compute partitions, we also make sure that they're reasonably well balanced so that all of the different computations end at the same time. So what will happen there is, once we have done that, then the data will actually be read from the external storage, computed on those partitions, and we will get the result back. So this is slightly different because the partition here is not defined by the actual cluster, but rather by the way that the data is stored on the external device. Okay, with that, I hope you have an idea of how we're basically are able to distribute the work onto those different partitions. So in Mike's presentation, he specified a few, or no, he mentioned a few properties that we have about isolation and scaling, and we said that basically we talk about the batch scale up and the transaction scale up. And so to evaluate if the things the properties that we're striving for, if they're actually achieved, we have designed a benchmark, and it's a benchmark for a hybrid system as we are. So you heard in the beginning, basically we have this combination of the operational side and the analytical side, and the fact that we can run those analytical queries on the operational data in real time. And so here we have a benchmark for these hybrid operational analytical systems. And it basically runs two workloads, which is an operational workload on the left and an analytical workload on the right. And the operational workload is inspired by TPCC, by the TPCC benchmark. And it basically runs a number of transactions that you see on the left continuously against the operational side of the system. And on the right, you see the queries, analytical queries that are also running at the same time in parallel. So basically, both workloads work at the same time and produce results together. And so the OLAP workload is also inspired by by a TCP benchmark, the TCP-H benchmark. And so we have created the CH benchmark consisting of C and 2 to be able to describe and validate systems in this way. And so when we actually ran this, what we did, we had 7 different configurations of Couchbase Server 7.0 to run these examples. So we have one example here that we're talking about. You see you have 9 nodes here. There are 4 at the top, which are the operational nodes, 4 at the bottom, which are the analytical nodes, and then there's one driver. And what happens when we use this system is that we take the operations that we have mentioned before on the CH2 benchmark and run it against the operational nodes, do the same for the analytical nodes, and then we measure what the performance is and what the behaviors are. And so what we see is that when you look at this graph, what you see is we're measuring the response time here for NewOrder transactions. That's one of the transactions that's being run and that is used as a measurement. And what you see, we have different combinations of nodes here with 4 operational nodes, 4 analytical nodes, 4 operational nodes, 8 analytical nodes, and so on. You can see that up there. And what you'll find out is that basically the whole transaction response time is determined by the number of operational nodes. So if you have 4 operational nodes, then you get a certain performance, and if you have 8, then you're twice as fast. So what you see here is we get wonderful linear transactional speedup. So that was one of the properties that we're looking for. There's another one which is very similar. So on the left side, we have no queries running at the same time. So this is basically a baseline case where we just run the transactions. And on the right side, we run queries at the same time in parallel. And what you see is between the left and the right side that the numbers are the same. The clustering is the same. Everything that's 4Q is in one cluster, and the 8Q is in one cluster, and you get the same doubling. So basically, you see no difference in the impact of running that additional query stream. And so it shows that we also achieve our goal of having an effective performance isolation. And finally, we, of course, also want to know what it means. So what is the performance that we can achieve when running those analytical queries that use our parallel evaluation engine? And here again, you see that the clustering is really determined by the layout of the cluster. So if we have 2 analytical nodes, then we take about 90 seconds to do that. If we double the number of analytical nodes, the time it needs to run gets halved to 44. And again, if we add 2, basically double again to 8 analytical nodes, we again halve the time. And so we also get the linear speedup that we're looking for. So basically, after Mike has explained the principles, here we see that the principles actually hold, and we get the numbers that we expect. So with that, what we've seen here is we're talking about Couchbase Analytics, which is a really nice complement for the query service. It supports complex ad hoc analytical queries over the same operational data at the same time. So on really current data. With that, it eliminates the need for ETL or extract, transform, and load. That is often the case in data analysis. So in the past, we have coined this as no ETL for no SQL. We've also seen kind of what a MPP storage and query processing architecture looks like under the hood and how the work is distributed across different partitions. We talked a little bit about our LSM-based shared storage, shared nothing storage architecture with local indexing. And we also showed how we can use partition parallelism when querying external data in addition to the internal data that we have queried before. So we see we have a really nice dual engine architecture here for performance isolation and independent scaling. And we have shown that this actually works. And we have a really rich SQL-like declarative query language over JSON that can run these queries at any scale by just adding more capacity or changing the size of the problem. And with that, here is the contact information. If you want to get more information from Mike or myself, you will have the email addresses here. And also, please visit couchbase.com on the web, or follow us on Twitter, or follow us on Facebook. With that, thank you very much. Have a good day.